Welcome to The Explainer. Today we're cracking open the architectural playbook for modern AI. We're going to look at the key design choices that have, come to define what a state-of-the-art language model even is. So, you might be wondering, what's actually going on inside an AI's brain? Well, let me tell you, it is not magic. It's actually a set of really powerful, battle-tested design principles. We're going to explore how researchers started with this whole zoo of different ideas and somehow ended up with a surprisingly consistent and, refined blueprint for building these things. And that's really the key here, right? This whole story is one of convergent evolution. We're going to learn from the collective wisdom of the entire field, basically how years and years of trial and error finally showed everyone what really works and what doesn't. Okay, so here's the plan. First, we'll tackle the foundation, how to make these things stable enough to even train. Then we'll get into the smarter components that make them tick, the magic numbers that guide their design. And finally, we'll take a little peek at what's coming next. All right, first things first. The biggest initial hurdle wasn't even about making these models smarter. It was just about making them stable enough to train in the first place. And this is where the first big agreement in the field really started to take shape. Okay, now look at this. It might seem like a tiny change, but this was huge. The original transformer did its math first, and then it normalized everything after. But folks pretty quickly figured out that if you just flipped that, if you normalize the data before it goes into the operation, everything becomes way, way more stable. And that's what we call pre-normalization, or pre-norm for short. And I mean, this wasn't just some small preference. It pretty much became an ironclad rule. Why? Well, pre-norm keeps the main data pathway super clean. Think of it like a perfectly paved highway for information. It lets the learning signals, what we call the gradients, just flow smoothly all the way through these incredibly deep networks without getting all messed up or, worse, just exploding. It was an absolute game changer. So once they figured out where to put the normalization, the next question was, can we make the normalization step itself better? And the answer was yes. The whole community pretty much shifted from the standard kind of heavy layer norm to this thing called RMS norm. It's basically a stripped-down, lean and mean version. It just gets rid of a couple of steps, which makes the whole thing a lot simpler and, crucially, a lot faster. So why did this simpler version win? I mean, this is the really interesting part. It turns out that performance isn't just about how many calculations you can do, the flops. A massive bottleneck, maybe the biggest one in modern computer chips, is just moving data around. And RMS norm is brilliant because it reduces how much data you have to shuffle back and forth. You're getting a major speed up. It's basically a free performance upgrade. And who doesn't love that? Okay, so the foundation is stable. The training isn't going to blow up. Now what? Well, now the focus could shift to actually upgrading the engine itself, making the individual parts inside the transformer smarter and more efficient. And one of the biggest upgrades came in the form of the activation function. See, older models use something simple like ReLU, which is kind of like a dumb on-off switch. But the field moved to these things called gated linear units, with the most popular one being SWIGLU. And you can really think of it like a smart, data-driven dimmer switch. It actually learns when to let a lot of information through and when to dial it back. It's a much more nuanced way of controlling information flow, and boy, has it proven to be effective. So this brings us to a really fundamental question. How in the world do you tell an AI what order the words are in? I mean, it's not obvious, right? Well, the answer that just about everyone landed on is this incredibly clever idea called rotary position embeddings, or ROPE. And yeah, it literally uses rotation to encode where a word is. And here's the magic trick. What ROPE is really good at is encoding relative position. By rotating each word's vector just a little bit based on its position, the angle between any two words always stays the same. So what does that mean? It means the model inherently understands that the phrase "we know" has the exact same meaning and relationship, whether it's at the start of a sentence, the middle of a paragraph, or the very end of a huge document. It's just brilliant. And this timeline really puts it all into perspective. I mean, look how fast this happened. We started with the original transformer in 2017. A few years later, the GPT-3 era brought in some key improvements. But then bam, around 2023, the Llama family of models really solidified this new consensus. They brought RMS norm, SWIGLU, and ROPE all together, and that pretty much became the new standard blueprint. All right, so we've got the ingredients, right? We know the components. But what about the recipe? It turns out there are these hidden rules of thumb. very specific numbers and ratios that AI architects use to put everything together. Okay, so for years, and I mean years, the standard rule was this. You take the feed-forward network inside your transformer block, and you make that middle layer exactly 4 times wider than the input and output. That 4x factor, that was just the way it was done. But then, remember SWIGLU? That smarter activation function? Well, it uses a few more parameters. So to keep the total model size roughly the same, the community adjusted that ratio down. The new magic number is about 2.67, or 8/3 if you want to be precise. This is a great example of how these design choices all connect. You get the benefits of the smarter activation without accidentally making your model way bigger. And then there's the classic question, should you build your model wider or should you build it deeper? Now, there's a little bit of wiggle room here, but a ton of research has pointed to a pretty clear sweet spot. A lot of the big, successful models we see today, from GPT-3 to Llama, have settled on this ratio of about 128 hidden dimensions for every single layer of depth. It just seems to be a really effective balance. So, that's the blueprint for today. But this field does not stand still. Not for a second. The evolution is absolutely not over. So let's take a quick peek over the horizon and see what's coming next. Okay, let's just quickly pull it all together. The blueprint for a modern LLM looks like this. You use prenorm to keep things from blowing up, you swap in RMS norm to make it faster, you use a smart activation like SWIGLU for better performance, you use rope so the model knows where words are, and one final detail, you generally remove these things called bias terms to, you guessed it, improve stability even more. That right there is the core toolkit. But as models get bigger, and I mean way bigger, new problems pop up, and so new tricks are needed. One of the latest is something called QK norm. It's basically adding another little normalization step, but this time it's hyper-focused, applied directly to the query in key vectors right inside the attention mechanism. It's all about taming that beast of numerical instability when you're training at truly massive scales. And here's another big one, but this is focused on a different problem. It's not about training the model, it's about running it, what we call inference. It's called Grouped Query Attention, or GQA, and it's a super clever efficiency hack. Instead of every part having its own dedicated resources, it groups them up so they can share. This massively cuts down on that memory movement we talked about before, which makes these models so much faster and cheaper to actually use in the real world. So there you have it. The blueprint is pretty clear, but it's written in pencil, not pen. It's constantly being revised. We've watched this incredible consensus form around a core set of ideas, all driven by this relentless hunt for more stability, better performance, and greater efficiency. Which really just leaves us with one big question to ponder, right? What comes next? What's going to be the next rope, the next prenorm, the breakthrough that redefines this entire field all over again?